Hello students, it's Usha from G.K.Jain High Secondary School. Today we are going to see Electrostatic Part 3 in 12th Standard Physics.
Electrostatic potential. Consider a positive charge Q kept fixed at the origin which produces an electric field E around it. A positive test charge Q dash is brought from point R to point P against the repulsive force between Q and Q dash, as shown in the diagram. Before I'm going into the electrostatic potential energy, we have to learn about the electric potential difference. It is the work done by an external force to bring unit positive charge from point R to P. So Vp minus Vr is equal to delta V, which is equal to integral P to R E dr vector. Now, what is electric potential? Electric potential at a point is equal to the work done by an external force to bring a unit positive charge with a constant velocity from infinity to that point in a region of the external electric field E. Vp is equal to minus integral infinity to P E vector into dr vector. Electric potential at a point P depends only on the electric field which is due to the source charge Q and not on the test charge Q dash. The practical unit is volt, named after Alessandro Volta, who invented the electrical battery. The next topic is electric potential due to an point charge. Consider a positive charge Q kept fixed at the origin. Let P be a point at a distance r from the charge Q. The electric potential at a point charge E is equal to the electric potential at a point P is V equal to integral minus infinity to R E into dr vector. If we substitute, the E value is equal to 1 by 4 pi epsilon naught Q by R square into R vector. V is equal to minus 1 by 4 pi epsilon, which is a constant, and the remaining will give it in the integral infinity to R Q by R square into R vector into dr vector. The infinitesimal displacement vector dr vector is equal to dr into r cap, and using r cap dot r cap is equal to 1, we have V is equal to minus 1 by 4 pi epsilon naught integral infinity to r Q by R square into dr. After the integration, V is equal to minus 1 by 4 pi epsilon naught into Q into minus 1 by R, applying the limits infinity to R. So 1 by infinity will be 0. So the final answer will be equal to 1 by 4 pi epsilon naught Q by R. So important points. If the source charge Q is positive, V is greater than 0. If Q is negative, then V is negative and equal to 1 by 4 pi epsilon naught minus Q by R. The description of motion of object using the concept of potential or potential energy is simple than that using the concept of field. It is clear that the potential due to positive charge decreases as the distance increases. But for the negative charge, the potential increases as the distance is increased. The electric potential at a point P due to the collection of charges Q1, Q2, Q3, etc. up to Qn is equal to the sum of the electric potential due to the individual charges. So V total is equal to 1 by 4 pi epsilon naught into summation I is equal to 1 to n Qi divided by Ri. Next, an important derivation, electrostatic potential at a point due to an electric dipole. Consider two equal and opposite charges separated by a small distance 2a. The point P is located at a distance r from the midpoint of the dipole. Let theta be the angle between the line OP and dipole axis AB. Let R1 be the distance of point P from plus Q and R2 be the distance of the point P from minus Q. Potential at P due to the charge plus Q will be given as 1 by 4 pi epsilon naught Q by R1. Potential at P due to the charge minus Q is equal to minus 1 by 4 pi epsilon naught Q by R2. When we have total potential, we have to add together. So V is equal to the constant terms, we'll take it outside, Q by 4 pi epsilon naught into 1 by R1 minus 1 by R2. Suppose if the point P is far away from the dipole such that R is very much greater than A, then the above equation can be expressed in terms of R. By the cosine law of triangle BOP, R1 square is equal to R square plus A square minus 2RA cos theta. Taking R square common from the terms, we have R1 square is equal to R square into 1 plus A square by R square minus 2A by R into cos theta. Since the point P is very far from dipole, R is very much greater than A. As a result, the term A square by R square is very small and that can be neglected. Therefore, R1 square is equal to R square into 1 minus 2A cos theta by R. Taking square root on both the sides, R1 is equal to R into 1 minus 2A by R cos theta the whole power 1 by 2. Taking the inverse of it, 1 by R1 is equal to 1 by R into 1 minus 2A by R into cos theta the whole power minus 1 by 2. So using our binomial theorem and retain the term up to the first order, 1 by R1 is equal to 1 by R into 1 plus A by R cos theta. Similarly, applying the cosine law for the triangle AOP, R2 square is equal to R square plus A square minus 2RA cos 180 minus theta. The 180 minus theta is the other side of the triangle, that's why we are going in for 180 minus theta. Since cos 180 minus theta is equal to minus cos theta, we have R2 square is equal to R square plus A square plus 2RA cos theta. Following the same procedure that we followed for R1 and taking the square root, binomial theorem, and we get 1 by R2 is equal to 1 by R into 1 minus A by cos theta divided by R. So the total energy total potential will be V is equal to Q by 4 pi epsilon naught into 1 by R into 1 plus A cos theta by R minus 1 by R into 1 minus A cos theta by R. So when we take the negative side inside for the second term, then we'll get 1 plus 1 and minus 1 will get cancelled. So you have V is equal to 1 by 4 pi epsilon naught 2AQ divided by R square into cos theta. But the electric dipole moment P is equal to 2QA and we get V is equal to 1 by 4 pi epsilon naught into P cos theta divided by R square. Now the special cases. If the point P lies on the axial line of the dipole on the side of plus Q, then theta is equal to 0, then the electric potential becomes V is equal to 1 by 4 pi epsilon naught P by R square. If the point P lies on the axial line of the dipole on the side of minus Q, then theta is equal to 180 degree, then V is equal to minus 1 by 4 pi epsilon naught P by R square. If the point P lies on the equatorial line of the dipole, then theta equal to 90 degree, then V is equal to 0. The next topic is equipotential surface. Consider a point P located at some point in space and an imaginary sphere of radius r is chosen by keeping the charge q at the center, which is shown in the first diagram. The electric potential at all points on the surface of the given sphere is the same. Such a surface is called as equipotential surface. So what is equipotential surface? An equipotential surface is a surface on which all the points are all on the same potential. For a given point charge, the equipotential surface or concentric sphere surfaces as shown in the second diagram. Each spherical surface an equipotential surface, but the value of the potential is different for different spherical surfaces. Next, if it is a set of planes as shown in the third diagram, the equipotential surface form a set of plane normal to the electric field E. Next, we are going into the relation between electric field and potential. Consider a positive charge Q kept fixed at the origin. To move a unit positive charge by a small distance dx in the electric field E, the work done is given by dW is equal to minus E into dx. The negative sign implies that the work done is against the electric field. So the work done is nothing but equal to the electric potential difference. So we have dW is equal to dV, or dV is equal to minus E into dx. Hence, E is equal to minus dV by dx. The electric field is the negative gradient of the electric potential. Electrostatic potential energy for collection of point charges. To calculate the total electrostatic potential energy, we use the following procedure. What we are going to do? We bring all the charges one by one and arrange them according to the configuration. Bringing a charge Q1 from infinity to the point A requires no work because there is no other charges already present in the vicinity of the charge Q1. To bring the second charge Q2 to the point B, work must be done against the electric field created by the charge Q1. So, the work done on the charge Q2 is W is equal to Q2 into V1B. Hence, V1B is the electrostatic potential due to the charge Q1 at point B. So, U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. Similarly, to bring the charge Q3 to the point C, work has to be done against the total electric field due to both charges, Q1 and Q2. So, the work done to bring the charges Q3 is Q3 into V1C plus V2C. Here, V1C is the electrostatic potential due to the charge Q1 at point C, and V2C is the electrostatic potential due to the charge Q2 at point C. The electric potential is U is equal to 1 by 4 pi epsilon naught into Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. So, by adding the total electrostatic potential energy for system of 3 charges will be given as U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. The total stored potential energy U is equal to the total external work done to assemble the 3 charges at the given location. The next topic is electrostatic potential energy of a dipole in a uniform electric field. Consider a dipole placed in a uniform electric field E. A dipole experiences a torque which kept in an uniform electric field E. This torque rotates the dipole to align it with the direction of the electric field. To rotate the dipole from its initial angle theta dash to the another angle theta against the torque exerted by the electric field, an equal and opposite external torque must be applied on the dipole. So the total work done to rotate the dipole from angle theta 1 to theta at constant angular velocity is W is equal to integral theta dash to theta tau external into d theta. Tau external is equal to P cross E, which when we substitute W is equal to integral theta dash to theta P sin theta into d theta. Integral of sin theta is minus cos theta. So W is equal to Pe into cos theta dash minus cos theta, which is U is equal to minus Pe cos theta, which is equal to minus P dot E. The total energy is maximum when the dipole is aligned anti-parallel, that is theta equal to pi to the external electric field, and minimum when the dipole is aligned parallel theta equal to 0 to the external electric field.
Thank you students. Once again we will meet you in the next video.